Deep in the constellation of Sagittarius lies a star so extreme it defies imagination. Bugyofarm 2, the hottest star ever recorded in the known universe. Its surface blazes hotter than any other, pushing the limits of what a star can be. If you enjoy exploring the cosmos, please like, subscribe and share, and tell us in the comments, what do you think could survive near a star like this? Thank you for watching. Now, let's begin. Toward the dense star fields of Sagittarius, the Milky Way thickens into a pale granular band, and the gaze moves along the galactic plane toward the central bulge, where the background brightens and dust lanes grow more intricate. In this direction, the sky's crowded because a shallow angle through the disk stacks many layers of stars and clouds along one line of sight. The setting is not a single neighborhood, but a long corridor through the inner galaxy, so every bright point lies in front of, within, or behind material that changes how its light arrives at Earth. Dark lanes of interstellar dust trace gentle curves across the crowded field, dividing the glow into irregular patches while clusters and knots ride between them like islands in a slow river. The visual impression is of depth and texture, a mix of bright star clouds and shadowed rifts that signal both the abundance of sources and the presence of intervening matter. This outer frame is the stage upon which a compact and intensely luminous star presents itself as a point-like beacon against a busy backdrop. Sagittarius is a two-dimensional guide on the sky, yet behind its familiar pattern stands the inner structure of the Milky Way. A rotating disk spiral features that gather gas, and stars a central bar that channels material inward, and a rounded bulge where stellar density rises. The sightline that crosses the teapot asterism also crosses low galactic latitudes, so it remains close to the plane. Low latitude paths intersect many clouds which shift the apparent colours of sources and dim their total light. Astronomers describe the colour change as reddening, and the dimming as extinction terms that reflect how dust scatters and absorbs shorter wavelengths more strongly than longer wavelengths. Correcting for these effects requires comparing observed colours with expected colours for stars of similar type, and using maps that estimate how much dust lies along a given direction. In such a corridor, a source may be intrinsically bright, yet appear modest, or it may seem redder than it truly is not, because it is cool but because dust has preferentially removed blue light from its spectrum. Wide-field surveys trace this corridor in many kinds of light. Infrared atlases reveal long, sinuous filaments where coal dust collects and breaks into knots under gravity. Radio maps of molecules trace lanes in which gas is dense and shielded the places from which future stars may form. Hydrogen line surveys mark shells and bubbles carved by energetic winds and older explosions, leaving curved edges and cavities that lace the disk. Ultraviolet catalogues highlight patches where radiation is strong and where gas is ionized, while X-ray images show hot, thin plasma, filling some of the cavities between denser clouds. Overlaid upon these maps are star clusters at different distances, some loose and old, others compact and young, each one contributing a local pattern of light that adds to the integrated glow of the background. From Earth, mountaintop observatories under clear and dry air gather long exposures that build faint structure out of the starry haze, while space-based platforms bypass atmospheric absorption and turbulence to examine the same field in ultraviolet, infrared and high-energy bands. The combined picture is one of alternating clarity and concealment. Bright star clouds mark sightlines that pass through many luminous sources with comparatively little obscuring dust, while dark rifts are foreground clouds that block background light and change the overall contrast of the field. The mixture of bright and dark features is not random. It reflects the way spiral structure organizes gas and dust into curved segments, and how the central bar steers streams of material into rings and lanes near the core. This organization sets the larger context for any individual source observed in this direction. Navigation within the crowded field uses two coordinate systems. Equatorial coordinates tie positions to Earth's rotation, and the celestial poles enabling repeated observations night after night with precise pointing. Galactic coordinates rotate that grid so that longitude runs along the plane of the Milky Way, and latitude measures angular distance away from the plane. The target star sits at a low galactic latitude, so it remains near the midline of the disk embedded in the busiest part of the sky as seen from Earth. Low latitude brings both advantages and challenges. It offers many comparison stars that share similar foreground screens, useful for calibration, but it also crowds the detector with near neighbours that can bleed into the same aperture if the pointing and image scale are not chosen with care. The broader environment extends to the dynamical centre further along the same general direction. Sagittarius A star, the compact radio source at the galactic centre, anchors orientation even when a target lies offset from that exact point. Toward the core, stellar densities rise and gas streams follow orbits shaped by the central bar gathering into rings where pressure is higher than in the outer disk. The inner regions show strong gradients in extinction across small angles on the sky, so a slight change in pointing can move a line of sight from a transparent window into a dusty lane. These gradients also mean that the foreground correction for any source must be handled locally, rather than borrowed from a distant patch. Seasonal and geographic factors on Earth complete the outer frame because they determine when and how the field is best observed. From mid-northern latitudes, Sagittarius climbs on warm nights and tracks low across the southern horizon, where the thicker slice of atmosphere softens images and increases extinction. From southern latitudes, the constellation rides higher, and the inner galaxy becomes a prominent overhead arch, allowing shorter atmospheric paths and steadier images. These geometric circumstances influence exposure times, filter choices, and scheduling of observations. They also help decide when to combine data from ground and space to balance resolution against coverage in different bands. Within this wide canvas, the target star is a point among many, but it carries a distinctive imprint in its light that allows it to be singled out. Surveys that sweep the inner disk mark its location, and follow-up catalogues record its coordinates, brightness in several bands, and the presence of strong emission features that distinguish it from the multitude of ordinary field stars. Its entry in these lists is not a narrative device, but a practical note on how such a source is found and revisited in a sky this busy. Around it, the field contains objects at many distances, foreground stars with measurable parallax clusters embedded in dust and diffuse patches of ionized gas that give a soft sheen to the background. Some features are physically related to structures nearer the core, and others are unrelated projections that simply share the same line of sight. All contribute to the layered appearance that defines this direction on the sky. The outer setting is therefore a structured, luminous and dusty corridor through the inner Milky Way towards Sagittarius, shaped by spiral patterns, the central bar and the crowded bulge. It is rich in stars and textured by clouds mapped by surveys across the spectrum, and observed from both Earth and space to separate foreground from background with patient incremental steps. Around the star, the surrounding interstellar medium shows the marks of strong radiation, working on gas and dust in a quiet but persistent way. Ionized hydrogen fills a volume whose size is set by the balance between photons that strip electrons from atoms and the slow rate at which those electrons find their way back. This region is not a hard shell, but a graded space in which ionization falls with increasing distance and with the growth of shadowed pockets behind denser clumps. The gas temperature in such ionized zones tends to settle near 10,000 Kelvin, set by a balance between the heating delivered by high-energy light and the cooling carried away by emission from common ions. In places where the gas is thinner, the temperature can ride higher because cooling is less efficient, while denser knots cool more readily and let a faint skin of neutral material survive on their shaded sides. The result is a gentle mosaic rather than a uniform glow. Radiation meets dust and gas unevenly because the medium is structured on many scales. Filaments run for many light years and then narrow to threads. Sheets billow and then fold into ripples guided by pressure differences and magnetic lines that thread the volume. Small clouds with enough density cast tapered wakes that remain partly neutral, even under strong irradiation, while their exposed faces evaporate and feed a slow flow of gas away from the clump. This process rounds sharp corners and softens edges so the observed shapes are smooth and continuous rather than jagged. Across the ionized volume, the chemical mix reflects past generations of stars that enrich the local gas with heavier elements. Oxygen, carbon, and nitrogen contribute to cooling through their characteristic lines, and their relative strengths help set the exact temperature at which the gas balances. The radiation field pushes on dust grains, nudging them outward from the brightest zones, and the smallest grains can be destroyed by energetic photons, reducing their contribution to extinction close to the star. Farther out, dust survives more easily and helps regulate temperature by absorbing and re-radiating energy in the infrared. The ionization front, where neutral gas yields to charged plasma, is not a single thin boundary, but a transition with layered behavior. Closest to the star atoms with tightly bound electrons can still be stripped, because the light is hardest there, and ions like doubly ionized oxygen become common. Farther out, only the most easily ionized species remain charged, and beyond that the medium returns to neutral. Density and homogeneities wrinkle this front into protrusions and recesses. Where the front advances into a lower density patch, it moves more quickly and pushes a shallow arc outward. Where it meets a denser clump, it slows and wraps around, creating pillar-like projections that point back toward the source. In the local medium, relic structures from earlier events may persist and be overwritten rather than erased. A faint shell from an older, slower wind or from a distant explosion can remain as a change in density into which the present radiation field and outflow now expand. When such a step in density is present, the ionized region becomes asymmetric, extending farther into low-density corridors and compressing against the denser side. This asymmetry reveals itself in arc brightness and in the shift of emission line strengths across the field. The gas motions within the ionized zone are gentle compared with the speeds reached by the stellar outflow, because most of the volume is pressure-driven rather than dominated by bulk streaming. Thermal motions at 10,000 Kelvin produce line widths of a few kilometers per second, for hydrogen broadened further by small-scale turbulence and by gradients along the line of sight. These widths record the local state, rather than any global expansion of the whole region. Where the radiation field meets denser clouds, photoevaporative flows lift off at roughly the sound speed in the warm gas and stream away, feeding the ionized volume from the edges. Magnetic fields frozen into the ionized plasma on these scales provide an additional tension that resists sharp bends and helps align filaments. Observationally, the ionized medium shows itself through a set of lines that carry most of the cooling. Hydrogen recombination lines trace places where electrons rejoin protons and cascade through energy levels, while lines from oxygen and nitrogen reveal the balance between heating and cooling. The relative brightness of these lines across the field tells how the temperature and ionization state change with distance and with the presence of dense clumps. In the infrared, forbidden lines from ions that do not radiate efficiently in collisions become significant, and their ratios help fix the electron density. Radio continuum emission adds a smooth background component that rises with the emission measure along the line of sight. Against this smooth signal, subtle features appear. Bright rims trace the illuminated faces of denser knots. Dimmer lanes mark the shadows behind them. Discrete arcs may indicate places where the outward pressure meets a density rise, and stalls building a slowly brightening boundary. If the star moves relative to the surrounding gas, the ionized region can become elongated with a compressed side that faces the direction of motion and an extended tail downstream, though in many cases the motion is small compared with the time needed to reshape the whole zone significantly. Beyond the ionized boundary, neutral gas continues and carries the imprint of both the current field and earlier shaping. Molecules survive in the densest cores, shielded by their own column density and by dust. At their surfaces, weak ultraviolet light can still dissociate fragile species, leaving layers where carbon is singly ionized and oxygen remains neutral, a mix that cools efficiently and can collect into thin sheets. Over long times, the interplay of ionization pressure and cooling can drive small changes in structure. Knots are eroded, filaments thin, and cavities widen. The net effect is a slow transfer of mass from denser clumps into the more diffuse ionized volume and then into the broader medium beyond as material mixes. This process does not move at a fixed pace but responds to local conditions, so different patches evolve at different rates. The local interstellar medium around such a source is therefore a living record of how strong radiation engages with the structured environment. It is bright where the medium is thin, and the ionization front runs cleanly, and it is intricate where density contrasts, and magnetic lines shape the path of light and gas. Each diagnostic band adds one layer of understanding optical lines for recombination and cooling infrared lines for density radio for smooth free emission and ultraviolet for the hardest parts of the field. Together they form a coherent though never perfectly uniform picture of a region, held in balance by heating, cooling, ionization and gentle flows, and they set the boundary conditions that the outflow encounters as it moves outward into space. From the immediate surroundings of the star outward, a continuous wind carries mass and momentum into space, at speeds of many thousands of kilometers per hour, rising to several thousands of kilometers per second once fully accelerated. This flow is not a gentle breeze but a dense, fast stream of ionized gas whose composition reflects a stripped evolved star rich in oxygen and carbon. The driver is light itself, photons leaving the compact hot source encounter ions that have many absorption lines in the ultraviolet. Each line offers a narrow doorway through which a photon can hand off a small push to an ion. Because the gas moves outward and gains speed, the lines are Doppler shifted, and fresh portions of the spectrum can be tapped for additional pushes as the flow accelerates. The result is a line-driven wind, a process in which the pressure from countless photons, each delivering a tiny impulse, adds up to a persistent force that lifts the gas and carries it outward. Near the star, density and radiation are both high, so the acceleration is rapid. The velocity grows from small values at the base to a large fraction of its terminal speed over a distance comparable to only a few stellar radii, although in a Wolf-Rayet wind the definition of a radius is model-based rather than tied to a sharp surface. A simple rule often used to describe such flows expresses speed as a smooth function that rises toward a fixed limit with increasing distance. The steepness of this rise depends on how many lines contribute and how effectively they can absorb light at each step in the acceleration. In a very hot wind where ions are highly stripped, the set of available lines shifts, yet the basic mechanism holds. The fast stream is not uniform. Small irregularities in density and velocity naturally amplify, because the force depends on local conditions. Where a pocket of gas is slightly denser, it absorbs a little more light, gains a stronger push, and briefly outruns its surroundings before colliding with slower material ahead. These interactions collect into shocks that heat small parcels of gas to temperatures high enough to emit soft X-rays, while most of the wind remains cooler and radiates in the optical and ultraviolet through broad emission lines. Clumping is the term used for this pattern of small-scale inhomogeneity. It increases the local density in the clumps compared with the average, and lowers the density in the spaces between them. Because many diagnostics depend on density in a non-linear way, the presence of clumps matters when mass loss is inferred from the strength of emission lines. Analyses therefore include a clumping factor to account for this structure, and the derived mass loss rates are adjusted accordingly. The wind's chemical signature appears across the spectrum. Broad lines from highly ionized oxygen and carbon dominate, shaped by the bulk motion and by the distribution of velocities along each line of sight. The breadth arises because gas parcels moving at different speeds and angles project a wide range of Doppler shifts into the observed light. The maximum width traces the terminal speed, while the detailed shape depends on how quickly the wind accelerates and how the density falls with radius. In some transitions, the profile includes a shallow absorption that dips below the continuum at blue shifted wavelengths and a rounded emission centered near the rest wavelength. This pattern APCINI profile records absorption of continuum light by gas, moving toward the observer, and re-emission in all directions by the excited ions, with geometry and velocity setting the balance between the two parts. The wind also carries momentum and energy into the surrounding medium. Far from the star, where the flow has reached a near constant speed, the density falls roughly as the square of the distance, so the ram pressure decreases with radius. The boundary at which this pressure meets that of the ambient gas fixes the size of an inner cavity and sets the conditions for a broader wind-shaped environment. Inside that boundary, the wind expands almost freely, and the gas is largely ballistic, moving on radial paths with only weak lateral forces. Magnetic fields frozen into the flow are stretched outward into a spiral pattern if the star rotates, although the degree of twist depends on rotation and on how quickly the wind accelerates. Observations of polarization place limits on large-scale asymmetry, suggesting that while small-scale clumps are common, the overall outflow remains close to spherical at the level that broad lines can probe. The temperature within the bulk of the wind is set by a balance of adiabatic cooling, as the gas expands radiative heating from the intense field of photons and cooling through line emission. In a very fast Wolf-Rayet wind, these processes maintain an ionization structure that changes smoothly with distance. Close-in ions with more electrons removed dominate. Farther out, where density and radiation field both decline, lower stages of ionization appear. This stratification means that different lines trace different zones of the flow, allowing tomography by spectroscopy when the data cover a wide range of transitions. Dust formation is not favored in such a hot oxygen-rich wind, both because the temperature is high and because the chemistry is not carbon-dominated in the way seen in some other types where dust has been observed. The flow, therefore, remains largely dust-free close to the star, reducing the chance for local extinction to complicate the emergent spectrum. The momentum carried by the wind relative to the light that drives it offers a consistency check on models. If every photon transfers only one push, There is a simple limit on the total momentum that can be delivered, but multiple scatterings on many lines allow the flow to exceed that limit in a controlled way, because a photon can be absorbed and re-emitted more than once as it climbs out through different velocity layers. In practice, sophisticated calculations track many lines and their overlaps to reproduce the observed speeds and mass fluxes with reasonable accuracy. Despite this progress, uncertainties remain, particularly in the exact degree of clumping and in the microphysics of how instabilities grow and merge into shocks. These uncertainties appear as ranges rather than precise numbers, and are noted as such when results are reported. The wind also imprints time variability on the spectrum. As clumps form, move, and dissipate, subtle changes ripple across the profiles of strong lines. Careful monitoring reveals migrating subfeatures that drift from lower to higher. Blue shifts, a sign of material moving outward and accelerating through the line-forming region. The timescales of these changes are short compared with the evolution of the star, reflecting dynamics within the flow rather than any deeper structural shift. Farther out, where the wind has reached a near constant speed and the density is low, collisions between clumps are rarer and the flow smooths into a more uniform stream. In all, the stellar wind zone is a realm defined by radiation pressure on spectral lines, by rapid acceleration to extreme speeds, by small-scale structure, born of intrinsic instabilities, and by a chemical mix that leaves clear spectral fingerprints. It is the mechanism by which the star sheds mass and interacts continuously with its surroundings, a bridge that carries processed material away, and sets the stage for the larger-scale structures that are seen beyond. Where the fast outflow meets the surrounding medium, a layered bubble develops that carries the marks of pressure, balance, cooling, and geometry. Closest to the star, the wind is free-streaming and supersonic, at a radius set by equality between the wind's ram pressure and the pressure of the interior cavity. The flow crosses a termination shock and slows, abruptly converting ordered kinetic energy into thermal energy. Post-shock wind becomes a thin, very hot plasma, with temperatures high enough to radiate soft X-rays, and because densities there are low, the cooling time is long, so the interior remains pressurized and pushes outward on the material ahead. This overpressure inflates a cavity whose boundary is a contact discontinuity, separating shocked wind from shocked ambient gas. Beyond that discontinuity lies a swept-up shell that gathers interstellar material into a compressed layer. A second outer shock runs ahead of this shell into gas that has not yet been disturbed, raising its temperature and beginning the compression that feeds the shell. In a uniform medium, idealized models separate these regions cleanly, but real bubbles in a structured environment show wrinkles, arcs, and breaks, where density and magnetic field change with direction. The size and expansion speed of the bubble depend on the wind's momentum and energy supply, and on the density of the surrounding gas. If radiative cooling in the swept-up shell is efficient, the shell collapses into a thin, bright rim, and the evolution becomes close to momentum-driven. If cooling is less efficient, and the hot interior retains most of its energy, the overpressure drives an energy-driven expansion, in which radius grows with time in a characteristic way, and the shell remains thicker. Observations look for signatures that reveal which regime dominates strong optical emission, and thin filaments suggest efficient cooling, while diffuse X-ray glow from the interior suggests stored thermal energy. Even in an energy-supported bubble, heat can leak from the interior through mixing layers and conduction at the contact discontinuity. Small perturbations grow as the shell pushes into the interstellar medium. Rayleigh-Taylor modes appear, where a dense shell rides on a lighter, hot interior, producing fingers and scalloped edges that face inward. Thin shell instabilities ripple the outer boundary, where small curvature differences focus pressure unevenly, and Kelvin-Helmholtz shear can roll up along surfaces where flows slip. These processes seed substructure that later marks the shell with beads, knots, and arcs, each one a small record of the local balance of forces. Where the ambient medium contains pre-existing filaments or clouds, the advancing front wraps around them and leaves protrusions and narrow pillars that point back toward the center. Photoevaporation brightens their faces while the mechanical pressure of the bubble erodes their sides. If the star has a measurable motion relative to the local gas, the bubble becomes asymmetric and may grade into a bow shape. The upstream side compresses and brightens, the downstream side stretches into a wake, and the termination shock shifts closer to the star on the compressed side. The degree of asymmetry gives a joint measure of stellar motion, wind momentum, and ambient density. Magnetic fields thread both the ambient gas and the bubble. In the low-density interior field lines are carried outward by the flow and draped along the contact, adding a restoring tension that limits the growth of some instabilities. In the shell field, amplification by compression and stretching increases the effective pressure and guides the direction of thin filaments. Polarization maps that trace aligned grains reveal large-scale field directions, while Faraday rotation of background radio sources probes the magnetized plasma along the line of sight and can hint at field strength within the shell and interior. Diagnostics across the spectrum outline each region. Optical lines from hydrogen and doubly ionized oxygen trace the bright cooled shell and pick out rims where the ionization front and shock front are close. Ratios of oxygen to nitrogen lines help measure temperature and density in the compressed layer. Infrared maps show warm dust in the shell where grains absorb ultraviolet and optical light and re-radiate in longer wavelengths. They can also reveal density enhancements at the edges of protrusions where dust collects. Radio-free emission gives a smoother view of ionized gas and helps estimate the total emission measure through the shell, while non-thermal radio arcs may indicate places where shocks accelerate electrons to high energies. X-ray images, when available, reveal a soft interior glow from the hot, shocked wind and spectra that constrain the temperature and composition of the cavity gas. Kinematics further fix the bubble's state. High-resolution spectroscopy of optical lines across the shell reveals a split-line profile in expanding segments, with the separation giving twice the expansion speed projected along the line of sight. Mapping this split around the rim uncovers the three-dimensional shape and any departures from spherical symmetry. Interferometric radio observations can trace slow drifts of the shell over years when expansion speeds are modest and distances are favorable. Combining these velocities with shell radius gives an age estimate, and together with the mass swept into the shell, a work budget that can be compared with the wind's output integrated over that time. In a crowded galactic field, superposition complicates interpretation because unrelated arcs or edges can lie along the same sightline. Careful registration across multiple bands and attention to consistent curvature and center of symmetry helps separate features at different distances. When the bubble expands into a medium with a strong density gradient, the shell thickens and slows on the dense side while running out into the thin side. Breakout can occur when the outer shock reaches a low-density corridor and accelerates, leaving an open chimney that vents hot gas into a larger, more tenuous volume. In that case, the interior pressure drops more rapidly, and the upstream shell can decelerate. Rebalancing follows as new mass is swept up and the interior heat content adjusts. The chemical composition of the shell records a mixture of ambient gas and a trace of wind material that has crossed the contact through mixing or at small breaches created by instabilities. In a wind that is rich in oxygen and carbon, Faint enhancements of these elements can appear in the inner parts of the shell, although abundance contrasts may be modest after mixing with a much larger mass of swept-up interstellar gas. Because densities are high in the shell compared with the interior, certain collisionally excited lines become efficient coolants and dominate energy loss, setting the shell temperature near a few times 10,000 Kelvin, with colder layers behind the shock if the shock speed falls. The bubble's life is tied to the wind source. As long as the mass loss and speed remain strong, the interior stays overpressured and the shell continues to move. If the wind weakens, the hot gas cools and the pressure falls and the shell coasts and then stalls as external pressure from the surrounding medium takes over. Subsequent flows can overrun the relic structure, producing nested arcs where new shocks cross old shells. In complex regions, multiple generations of winds and older explosions overlap, leaving a palimpsest of edges at different radii. Careful age dating through expansion speeds and surface brightness helps order these layers and identify the part connected to the present source. Even without perfect symmetry or isolation, the wind-blown bubble provides a readable map of interaction. It shows the reach of the outflow through its radius, the momentum and energy supply through its expansion, the character of the ambient medium through its asymmetries, and the presence of magnetic structure through its filament pattern. It remains dynamic on timescales of thousands to tens of thousands of years long. Compared with day-to-day spectral changes in the accelerating wind, but short compared with the broader evolution of the star, so. Repeated imaging over human times can register slow motion at the edges and track how substructures brighten or fade as local balance shift within the layered system. In the outer emission region, the light carries clear fingerprints of extreme ionization, and those fingerprints arise across a broad expanding volume rather than on a compact solid boundary. Gas here is thin enough for photons to travel long distances, but still dense enough for countless atomic encounters, so excitation and recombination proceed without pause. At these radii, the radiation field remains intense and hard, capable of stripping many electrons from heavy elements. Ions of oxygen and carbon in high stages of ionization dominate the cooling and radiative output, and their strongest transitions appear as broad features whose rounded shapes record the wind's full spread of outward speeds. The breadth of these features is not a property of thermal motion alone. It arises primarily because parcels of gas move at many velocities and project different Doppler shifts toward the observer. Where a line forms throughout a large radial range, its profile becomes a smooth, wide band of light centered near the laboratory wavelength but stretched on both sides. In some lines, a shallow dip appears on the blue side. This is where outward moving gas absorbs a small fraction of the star's underlying continuum, before re-emitting, producing the characteristic hollow that accompanies an emitting envelope seen in bulk expansion. In the outer emission region, the continuum itself is not limited to starlight filtered through a shell. Free electrons scatter light and smear sharp features into gentle wings, while free and bound free processes add a smooth background that rises with wavelength, in a way set by temperature and density. Because electron scattering is nearly grey, it broadens the cores of strong lines into low-level skirts that fade gradually rather than ending abruptly. These skirts carry information about the number of scatterings and thus about the column of electrons along the line of sight. The temperature of the gas in this region is not the same quantity as the effective temperature used to summarize the star's radiant output. Here local heating comes from absorption of energetic photons and from the dissipation of small shocks seeded by instabilities in the accelerating flow, while cooling proceeds through radiation in many lines. In steady conditions, the temperature settles into the range where heating balances these losses, and for a thin, highly ionized mix, the result is several tens of thousands of degrees. That balance changes slowly with radius, as the radiation field weakens and the density falls, so the emissivity of each ion shifts outward or inward according to how easily it can be excited or how quickly it recombines. The geometry of emission is set by the wind's nearly spherical flow. Photons born at one radius and direction must pass through other layers with different speeds and ionization states before they escape. Where the line of sight crosses large path lengths at nearly constant projected velocity, the contribution to the profile is greater, and this geometric weighting helps explain the rounded, often flat-topped appearance of strong features. If clumps are present, and they almost always are in a line-driven wind, they increase local density, and thus increase the rate of processes that depend on collisions. This boosts line brightness for a given average mass loss, and requires that analyses include a correction for the degree of clumping when inferring global flow rates. Without that correction, the wind could appear heavier than it is. Diagnostics across the electromagnetic spectrum divide labour within this region. Optical transitions from doubly and triply ionized species shape the most prominent features in visible light. Ultraviolet lines from even higher stages respond to the hardest part of the field, and probe zones closest to the star where ionization is more complete. In the infrared fine structure, transitions of abundant ions carry away energy efficiently at lower densities and offer density measurements through well-understood ratios. Radio free emission provides a smooth, slowly varying continuum that scales with the square of density integrated along the line of sight, so it responds strongly to the total mass within the outer region. Together, these bands allow mapping of ionization and density with radius, when observations are taken at sufficient resolution and signal. The outer emission region also records scattering on dust if grains are present, but in this environment dust is scarce because the gas is very hot, and oxygen-rich conditions that do not favour grain survival or growth. As a result, most of the scattering is by electrons, and polarization from that scattering remains small if the outflow is close to spherical. Small departures from symmetry can leave a residual polarization that varies slowly with wavelength. Monitoring that signal places limits on large-scale asymmetry in the line-forming volume. Time variability within this region arises naturally from the passage of clumps, and from changes in the network of weak shocks that ride with them. Over hours to days, the troughs and shoulders of strong lines show migrating ripples that drift toward higher blue shifts as the material that imprints them accelerates outward. These sub-features do not signal a change in the star itself. They are signatures of dynamics within the flow. Because the outer emission region spans a large radius range, many such ripples coexist, and the integrated effect is a gentle breathing of profiles rather than abrupt switches. The concept of a surface requires careful language in this kind of star because the gas is expanding and thick to its own radiation over a great depth. A familiar photosphere defined as a thin layer where light escapes does not exist as a distinct sharp boundary. Instead, there is a model-dependent layer where the atmosphere transitions from largely opaque to more transparent for the wavelengths that carry most of the visible light. In practice, the zone that contributes most of the observed continuum and the zones that contribute the strongest lines overlap but are not the same. Lines sample a range of radii where the relevant ions are abundant, and where collisions and radiation have the right balance to make emission efficient. The continuum samples the depth, where the material ceases to act like a fog and begins to let light stream more freely. Clarifying this distinction prevents the outer emission region from being misinterpreted as a skin that coats a solid body. It is a luminous, stratified envelope through which light and matter exchange energy across considerable radial distance. Kinematics from high-resolution spectroscopy refine this picture. The width of the broadest lines indicates the terminal speed reached by the outflow, while the curvature of the line wings reflects how quickly acceleration saturates. The relative weights of blue and red halves of a profile reveal whether occultation by the inner wind suppresses emission from the far side. In a nearly spherical extended envelope, the red wing is slightly diminished because parts of the receding flow are hidden. Electron scattering wings extend beyond the main Doppler core and fall off gradually, a sign that some photons have wandered through a few large deflections before escaping. Line ratios within a family of transitions act as thermometers and barometers with specific pairs sensitive to electron temperature or density. Interpreting those ratios requires models that include departures from local thermodynamic balance, because the radiation field is strong and collisions are not always frequent enough to enforce a simple equilibrium. Such models, when constrained by observations across many bands, yield consistent temperatures for the gas and credible mass loss rates for the flow. Over larger distances within this region, the density falls roughly as the inverse square of the radius, so emission measures drop rapidly. This decline makes the outer edges of strong lines sensitive to the presence of extended low-density gas. If a faint plateau extends farther in velocity than expected, it can indicate weak emission from parcels that have reached full speed and now glide outward in the thinnest parts of the envelope. Conversely, a sharper than expected cutoff can mark where ionization changes leave too few of a given ion to contribute at that velocity. In all these ways, the outer emission region functions as a readable archive of the wind's conditions, density structure recorded as line strength and shape ionization state, expressed as the mix of species that shine and scattering depth, written into the wings that frame the features. Each spectrum is a snapshot of that archive at one time, and a sequence of spectra builds a quiet chronicle of how a bright hot star lets energy and matter pass through a wide radiant volume before they continue outward into space. The atmosphere of this star is an expanding ionized envelope with no single sharp boundary, and its layers are defined by how light interacts with gas that thins smoothly with distance. In such an envelope, temperature, density, and ionization change together in a steady outflow, so layers are best understood as zones where particular processes dominate, rather than as shells with fixed edges. Model atmospheres for this kind of object treat radiation and matter together because collisions alone are not frequent enough to set a simple equilibrium. The radiation field is intense, the gas is thin, and many important energy levels are populated by light rather than by random impacts, so the usual shorthand of a local thermal balance does not apply. Instead, the population of each level and the ionization of each element follow from a balance among absorption-emission and scattering combined with the motion of the wind. The term effective temperature appears often in descriptions of hot stars and has a specific meaning. It is the temperature that a perfect black surface would need so that over all wavelengths it would emit the same total energy per unit area as the star radiates where the light effectively escapes. In a compact expanding envelope, this number is a way to summarize the radiant output, but it does not mark a physical layer at a single radius. It is a property of the model that best reproduces the spectrum rather than a thermometer reading at one surface. For this, star analyses place the effective temperature near 200,000 Kelvin, with similar WO-type stars clustering within a range of roughly 150,000 to a little over 200,000 Kelvin, and the scatter reflects real differences and the limits of present methods. Within the atmosphere, ionization is extreme, close in, and softens with radius. Near the base, helium is largely doubly ionized oxygen, and carbon are stripped to high stages and free electrons are abundant. Farther out, the radiation field weakens as it spreads, collisions become less frequent, and recombination steps bring some ions to lower stages. This graded ionization structure is what gives the spectrum its mix of very high and somewhat lower excitation features. The same structure governs where each strong line forms, because an ion contributes light most efficiently where it is common and where densities and temperatures make its transitions likely. The temperature profile follows a balance that includes adiabatic cooling due to expansion, radiative heating from the flow of photons through the gas, and radiative cooling as the gas emits in many lines. The result is not a single value but a smooth curve in which temperature declines with distance through the atmosphere, while remaining high enough to keep heavy elements in high stages of ionization over a broad range. Density falls with radius more steeply than temperature, because the wind accelerates while mass flow remains constant, so the same amount of matter crosses each spherical surface per unit time, but is spread over ever larger areas at higher speeds. This decline controls the optical depth, which is the measure of how many interactions a photon is likely to have before it escapes. Deep in the atmosphere, the optical depth is large, and light is trapped, scattering many times and sharing energy with the gas. Farther out, the optical depth falls to near unity in the wavelengths that carry most of the visible light, and beyond that the gas becomes effectively transparent, because different wavelengths see different mixtures of ions and electrons. This transition happens over a depth rather than at a single surface. Opacity within the atmosphere comes from several sources. Electron scattering provides a nearly grey background that does not favour one wavelength strongly over another. Bound-free and free-free processes contribute a smooth rise in opacity toward longer wavelengths under these conditions. Most striking, however, is the opacity in countless ultraviolet lines of oxygen, carbon, and helium. Each line is a narrow gate that can absorb a photon and re-emit it in a direction that changes from the original path or redistribute its energy among other lines. The wealth of these lines shapes the flow of energy and helps drive the wind. They also shadow their neighbours because the outflowing gas Doppler shifts each interaction into or out of resonance as the photon climbs through layers of increasing speed. This shift is what allows many lines to act together, handing off the photon's push from one set of ions to another as the gas accelerates. Because the atmosphere is expanding, geometry matters for how light escapes. A photon aimed outward from a given point sees a different set of velocities and opacities than a photon emitted sideways, so escape probabilities depend on direction. That directional dependence imprints itself on line profiles and on the smooth continuum wings that arise from electron scattering. Sophisticated models account for this by solving radiation transport along many rays through a velocity field that is prescribed by the momentum balance between radiation and gravity. The ratio of outward force from radiation to inward pull from gravity is near unity in these stars as expected, when light itself is the chief mover of the gas, and the competition is settled in favour of a steady outflow, because countless lines multiply the effect of the photon field. At the microscopic level, small perturbations in flow and ionization appear and grow. A slightly denser patch absorbs more light, gains extra push, and accelerates while the region behind it absorbs less and lags. The faster patch runs into slower gas ahead, and a weak shock forms. These events convert a small fraction of flow energy into heat and soft X-rays, while most of the atmosphere continues to radiate strongly in optical and ultraviolet lines. The cumulative result is a clumped structure, in which the mean density is low, but local density can be higher in small parcels. This clumping touches every diagnostic that depends on density, and must be included when inferring mass loss temperature and ionization from the emergent spectrum. Helium, oxygen, and carbon dominate the composition throughout the atmosphere, because the outer layers of the original star have been lost. Hydrogen is weak or absent in the spectrum, consistent with a deeply stripped advanced state. The relative strengths of lines from oxygen and carbon serve as indicators of both composition and temperature in the layers where they form. Ratios between lines that share a common upper or lower level act as density or temperature probes, although interpretation requires careful modelling because departures from local thermal balance are strong. Observations in the infrared provide additional leverage because fine structure lines are sensitive to electron density in ranges lower than those probed by optical transitions, and they emerge from zones farther out where the atmosphere becomes more transparent. Across the whole structure, the spectrum records not only the current state, but also slow variations as the atmosphere responds to changes in flow on small scales. Migrating subfeatures in broad lines reflect parcels of gas moving through the layers where those lines are most efficient. Gentle drifts in polarization can appear if the larger scale shape of the flow departs slightly from perfect spherical symmetry. When present, these changes move on timescales of hours to days, which are short compared with the overall evolution of the star and long compared with the time a photon takes to escape once it reaches regions of low optical depth. All of these properties, from ionization stratification and temperature decline to density fall-off and clumped structure, work together to build an atmosphere that is both luminous and dynamic. It is transparent enough for light to carry detailed information outward, yet thick enough over a great depth that the concept of a single surface is a simplification. It is thin enough in density that light controls the populations of many energy levels, yet rich enough in ions and electrons that millions of interactions per second shape the emerging spectrum in every small volume. Within this broad expanding envelope, each layer is defined not by a sharp boundary, but by the balance of forces and processes that set what light is produced and how it escapes into space. The notional layer from which most visible light escapes is a zone defined by how opaque the atmosphere remains to its own radiation, not a solid boundary or a thin skin. In a classical star with a stable, slow atmosphere, the photosphere is a narrow layer where gas becomes transparent over a short distance, so light rises from almost the same depth at all directions and wavelengths. In this star, the gas expands swiftly, carries large velocity gradients, and stays thick to scattering and line absorption over a great depth, so the layer of last effective interaction spreads across many radii and shifts with wavelength and direction. The practical measure of this layer is optical depth near unity, a phrase that means photons have on average about one significant interaction left before they escape. Because the outflow accelerates and the density drops outward, the place where this condition is met marches through the envelope according to how easily a given wavelength interacts with the ions and electrons along the way. Where line opacity is strong, the zone of escape sits farther from the center, and where the continuum is grey and thin, the zone nests deeper. The result is a family of frequency-dependent release surfaces rather than a single photospheric shell. Electron scattering contributes a background that is nearly the same at all visible wavelengths, so it sets a broad baseline for opacity that remains important even where true absorption is weak. Every scattering event changes a photon's direction, and slightly reshuffles its energy budget so multiple scatterings blur sharp features into smooth wings and let photons wander before they find a path outward. This wandering means that the intensity seen at any angle comes from an average over a range of depths, rather than from one thin layer. In a static photosphere of a cool star limb darkening appears because sightlines that graze the surface pass through cooler upper layers, while a view straight down reaches deeper, hotter gas. Here the atmosphere is hot ionized and moving, and electron scattering replaces much of the simple absorption. The angular pattern becomes gentle, and can even look more uniform across the disk in models that form a projected image because scattering tends to equalize brightness over angle. The moving medium introduces an additional geometric effect. As gas accelerates outward, the resonance condition for a line shifts with position. A photon that is slightly off resonance at one radius can find itself exactly on resonance at the next or the reverse, as the Doppler shift brings ions into or out of tune. This layered tuning lets different shells contribute to the same wavelength in different directions, and it alters the shape of the release surface for each line. Emergent profiles then reflect both the distribution of last interactions in space and the range of velocities at those places. The continuum, which is dominated by electron scattering and bound free and free-free processes, emerges from deeper layers, where interactions are frequent, but not so frequent that photons are trapped indefinitely. In that region, the radiation field and the gas share energy through repeated scatterings and absorptions until the statistics favor outward flight, and the angular pattern approaches the smooth shape that a thick scattering medium produces. Because the definition of the layer of escape depends on wavelength, a single radius cannot describe the star's visible size. If an image could be taken through a narrow filter placed on a strong line, the apparent radius would be larger than through a filter placed on a clean piece of continuum. Interferometric measurements at different wavelengths can in principle see this change in size, and models predict a slow outward drift in apparent radius as the filter moves into stronger opacity. This behavior is a hallmark of a pseudo-photosphere formed in an outflow rather than a classical thin photosphere attached to a hydrostatic layer. Temperature at the layer of escape is not equal to the effective temperature that summarizes the total radiant output. The gas there has a local temperature set by balance among adiabatic cooling, radiative heating, and radiative cooling in lines, and this temperature declines with radius. The intensity that emerges is set by the source function, a term that summarizes how emission and scattering populate the beam at each point. In a scattering-dominated medium, the source function couples to the mean intensity of radiation more than to the local gas temperature, so the continuum looks like a softened version of deeper, hotter layers, blended by multiple scatterings. Lines break that smoothness where true absorption or emission departs from the background, and those departures remain broad because velocity spreads across the release region are large. The layer of escape is time-dependent on small scales because clumps travel through it. As a dense parcel rises, it locally increases opacity, nudging the release surface to a slightly larger radius along that sight line and deepening a small part of a blue wing where absorption grows. As the parcel accelerates, its imprint migrates in wavelength and angle. These ripples ride on top of a steady background and fade as the parcel expands and mixes. Because many parcels move at once, the net effect is a patterned but gentle variability of the line cores and wings, and a low amplitude flicker in the continuum. The steep drop of density with radius and the near spherical symmetry on large scales mean that occultation matters for radiation from the far side. Photons from receding gas can be absorbed or scattered by closer layers before they reach the observer, reducing the weight of the red wing of an emission feature and shifting the apparent balance slightly toward the blue. In a thin classical photosphere, such occultation affects narrow cores modestly. Here it shapes broad pass bands because the release region is deep extended and filled with moving material that feeds both emission and absorption along many paths. The radius often quoted for a Wolf-Rayet star is by necessity a model-dependent construct, tied to where the optical depth in the visible reaches unity when averaged over the relevant processes. This radius is smaller in hard ultraviolet, where fewer lines remain to catch photons, and larger in optical bands where the forest of lines and the scattering background together hold light longer. Any comparison to the radius of a cool, slowly rotating star must be made with care because the physical meanings differ. In the cool star, the radius marks a thin, well-defined layer. Here it marks the inner boundary of an extended release zone, through which light still scatters several times before leaving. Observational strategies exploit these properties. High-resolution spectra split the broad features and reveal how the wings fall, a measure of the blend between Doppler broadening and electron scattering. Polarimetry tests for residual asymmetry in the release layer by measuring a tiny preferred orientation of the emergent light that would appear if the last interactions occur more often in one direction. Interferometry near strong lines checks for a change in apparent size that tracks the depth of the line and the position of the formation region. Each method cross-checks the others and ties the model definition of the release layer to measurable quantities. The optical depth unity concept also governs how energy flows upward through the atmosphere. Below the release zone, photons are trapped long enough that radiation and gas share energy closely, and small temperature gradients can carry a large flux without steep rises in brightness. Above it, photons stream freely, and the intensity responds directly to local conditions. The transition is gradual because different wavelengths decouple at different depths. Accurate modelling must solve radiation transport through the moving gas with many lines, and a realistic scattering background, and then adjust the density and velocity structure until the emergent spectrum and angular patterns match observations across many bands. In this framework, the optical depth layer is not an added surface, but a consequence of the full structure. It is the locus where light, after a long sequence of interactions in a fast ionized envelope, finally finds more paths outward than back, and the details of its shape and position are written into every broad line, every smooth wing, and every subtle change of apparent size across the visible range. Beneath the frequency-dependent release zone, the gas remains optically thick enough that radiation and matter stay closely coupled and transport proceeds mainly by diffusion rather than by free streaming. In this compact envelope, the pressure from light outweighs the pressure from particles over much of the depth, so the gradient that carries energy outward is set by how efficiently opacity hinders the flow of photons. The gas is fully ionized in these layers, and the composition is dominated by helium, oxygen, and carbon, with hydrogen scarce or absent. Opacity arises from electron scattering from bound free edges of highly ionized heavy elements, and from a dense forest of lines in the ultraviolet that blend into an effective background. The Roslin mean opacity, which weights lower opacities more strongly, because those channels carry most of the flux, acts as the summary quantity that connects the local gradient of temperature to the needed radiant flux. Where this mean rises, the temperature gradient steepens to deliver the same energy, and where it falls, the gradient can relax. Gravity pulls inward, and radiation pushes outward, and their ratio is close to unity here. That near balance makes the structure sensitive to small changes in opacity. If opacity increases with temperature over some interval, the gradient can steepen until convection would normally begin in a cooler star. In these hot ionized layers, the high radiation pressure and the strong coupling between light and matter suppress classic efficient convection, so any overturn that appears is likely inefficient and limited in scale. Models treat this region as radiative, with only mild departures where local instabilities may stir. Even when the flow remains radiative, the near equality of outward and inward forces can produce shallow density inversions, or a small inflation of the envelope where a modest thickness grows at nearly constant temperature to keep the outward flux moving. The presence and extent of such features depend on the exact composition and the microphysics of opacity, and different calculations explore ranges that still fit the observed spectrum. Temperature declines inward through these layers more slowly than in a cool star because radiation pressure supports much of the weight. Gas pressure remains present and provides stability against abrupt collapse, but its share of the total is small compared with the pressure carried by photons. The sound speed follows from the mix of pressures and stays high, while the physical scale height, which measures how quickly density falls with radius, is small because gravity is strong in a compact star. The result is a steep rise of density over a small radial step as one moves inward, coupled with only a gentle rise in temperature compared with the drop felt higher up. The diffusion of radiation converts many short steps of scattering and absorption into a net outward drift of energy. In each small volume, photons scatter countless times, nudging their way through a medium that is only partly opaque at any single wavelength, but thick when many interactions are counted. The approximation that treats the flow of energy as proportional to the gradient of radiation energy density holds well where the mean free path is short compared with the scale over which conditions change. Closer to the release zone, this approximation weakens, but in the subphotospheric envelope, it remains useful and connects local quantities in a simple way that still honors the complexity of the opacity mix through the Roslon mean. Gradients in chemical composition across this region are expected to be small because the atmosphere above is already dominated by processed material. Microscopic diffusion that would separate species is overwhelmed by the strong radiation field and by turbulence seeded by weak instabilities, so the composition remains nearly uniform across the thickness relevant to transport. Any residual stratification would be subtle and hard to measure directly, and present data do not demand it. Stability against large-scale pulsation is aided by the strongly radiative character of the envelope. When a layer is compressed, radiation pressure rises quickly and pushes back, and when it expands, the stored radiation energy density drops and the push slackens. This feedback reduces the growth of large amplitude oscillations under these conditions. Small amplitude variability may still appear as the surface responds to dynamics in the overlying wind, but those signals do not require deep structural change in the subphotospheric layers. The velocity field remains subsonic throughout this zone because the organized outflow is not yet accelerated into the supersonic regime. The dominant motion is the slow outward drift required to feed the mass into the wind above, with speed set by continuity between the mass loss rate and the area through which material must pass. Viscous and radiative damping suppress shear on large scales, so turbulence is expected to be moderate and localized if present. Any small-scale stirring that arises from local opacity peaks acts mainly to mix parcels and smooth gradients. Magnetic fields, if present, are carried with the ionized gas, and can contribute a small additional pressure. In these layers, the field is likely too weak to reorganize the structure against the combined weight of gravity and radiation, but it can guide minor anisotropies and influence where small eddies form and dissipate. The degree of field influence remains uncertain because direct measurements are challenging in such hot dense and bright environments, and model fits to spectra. Place only loose bounds on large-scale field strength. The link between this envelope and the spectrum that emerges above is tight yet indirect. The envelope sets the continuum brightness and the angular distribution of light that rises into the line-forming regions. It establishes the temperature and density conditions at the base of the wind, which in turn fix the ionization pattern and acceleration efficiency in the expanding atmosphere. Because the envelope is optically thick, small changes in its opacity or temperature gradient can shift, where photons decouple by a small fraction of a radius, and that shift changes the relative weights of line and continuum in the next zone outward. In practice, models converge on envelopes that deliver the observed continuum slope and polarization, while providing boundary conditions that allow the wind to reach the measured speeds and reproduce the line ratios. Uncertainties center on the exact opacity structure at very high temperatures, where many lines overlap, and on the role of microclumping that might extend inward. These are handled by exploring families of solutions that match the data within stated bounds rather than by insisting on a single exact structure. Energy conservation across the envelope provides a steady reference. The luminosity remains practically constant with radius through these layers, because local sources and sinks are small compared with the flux carried outward. That constancy ties temperature, gradient, opacity, and density together, and it lets independent checks from different wavelength bands reinforce one another. Ultraviolet and optical continua constrain the run of temperature through the outermost part of the envelope, while infrared slopes tie into the free background that rises from deeper, denser regions when seen through the thinning overlying atmosphere. Each piece fits only one range of depth, so only a combined view draws the full profile. In the sub-photospheric zone of a stripped, extremely hot star, the physical picture that emerges is one of a radiatively supported diffusion dominated envelope with high radiation pressure, steep density gradients, gentle temperature decline and composition, dominated by helium, oxygen, and carbon. Transport is controlled by a complex temperature-sensitive opacity, whose small changes matter because of the near balance between push and pull. Convection, if present at all, is limited and inefficient, and large-scale pulsations are damped by the same coupling that makes radiation the chief carrier of energy. The envelope feeds the outflow above by setting the boundary conditions at which the accelerating wind takes over, and it shapes the continuum against which broad emission features are seen, all while remaining a zone where light and matter remain intertwined across many interactions, before the first true steps toward free escape begin. Deep inside energy comes from nuclear reactions that proceed in shells rather than in a single broad zone, and those shells reflect the star's advanced state. In a stripped, very hot object of this class, the outer layers show the products of earlier helium fusion, so the light elements have been reduced, and the surface is rich in carbon and oxygen. That surface chemistry implies that helium burning has largely run its course, and that the interior has moved on to stages where heavier nuclei take part. The geometric picture of burning shells uses a layered arrangement set by temperature and density. Gravity compresses the deepest regions to high densities and heats them strongly, and the temperature drops outward over short distances. Each fusion process requires a threshold in both temperature and density to overcome the electrical repulsion between nuclei, so the hottest central zone can support the most demanding reactions, while slightly cooler layers just above it support reactions with lower thresholds. The outcome is a stack of active regions, each one narrow compared with the star's overall radius, each one surrounding the deeper shells and feeding on the ashes of those burning below. In a highly evolved, very massive star, the deepest active zone is expected to support oxygen or silicon fusion, depending on the precise stage reached, while an overlying shell may burn neon or oxygen, and a still higher shell burns carbon. Above those layers, if fuel remains, a thin shell of helium burning may persist, but in a stripped star this shell is expected to be weak because helium has already been consumed in earlier phases. Hydrogen burning is absent in such an interior because the outer envelope that once held hydrogen has been lost, and the deeper layers are too hot and too dense for that low temperature process to remain relevant. The structure within each shell involves a competition between energy generation and cooling. Nuclear burning adds heat locally, and the star carries that energy outward mainly by radiation. In the deepest zones, neutrino emission becomes an important sink. Neutrinos are nearly non-interacting particles produced in high-temperature reactions and in processes that occur in dense hot matter. Because they escape almost without interacting, they drain energy rapidly from regions where they are produced, and that loss forces higher nuclear reaction rates to maintain the outward energy flow. As the star advances through late stages, neutrino cooling grows so strong in the hottest layers that it dominates the energy balance. The shells adapt by thinning and by confining their active zones to narrow ranges in radius, where the conditions match the requirements of each reaction network. Within a carbon-burning shell, carbon nuclei combine to produce neon sodium and magnesium, along with free particles that carry away some energy. In oxygen, burning oxygen nuclei fuse to form silicon-sulfur and other intermediate mass elements. In silicon burning, which proceeds at still higher temperature, a network of nuclear rearrangements drives matter toward an ion group mixture. These processes do not proceed in isolation. They are embedded in a sea of radiation and electrons where the state of ionization is complete, and where electron degeneracy can begin to influence the pressure in the deepest layers. The star remains supported mainly by radiation pressure in the layers above, but in the core region electron pressure adds to that support as densities climb. The timescales of these shells shorten, as the reactions involve heavier nuclei because the temperature sensitivity of the rates is very strong. A small increase in temperature greatly increases the reaction rate, so once a shell is active, it can consume its fuel in a period far shorter than the long eras of hydrogen or helium burning that precede these late stages. For a single star, these late steps pass quickly in astronomical terms, yet they remain long compared with the time light takes to cross the star, so the structure can adjust quasi-steadily to the demands of transport and pressure balance. The arrangement of shells is not static. As fuel is consumed in one layer, the shell can migrate inward in mass coordinate following the boundary where the needed temperature and density occur. New shells can ignite above as ashes from deeper burning heat and compress overlying material. The result is an onion-like stack in which multiple shells can be active at once, each one narrow, each one feeding heat into the surrounding matter. Because the star is already stripped, these inner adjustments do not greatly change the surface composition on short timescales, though slow changes in wind composition can appear as deeper processed material is mixed outward by the strong flow and by turbulent motions near the base. Mixing between shells remains limited by strong stratification. The gradients of mean molecular weight and temperature make large-scale convection unlikely in the hottest layers of a star where radiation pressure dominates, though smaller scale mixing can occur near boundaries where the opacity changes or where weak shear develops. Models therefore include overshoot and semi-convective prescriptions to capture limited exchange across layer interfaces, yet they maintain distinct burning zones because the steep thermal requirements keep the core organized by temperature. The energy that leaves these shells flows outward through the radiative envelope described earlier and sets the luminosity that the wind must carry. Because neutrino cooling removes energy silently from the deepest zones, the surface luminosity does not track the total power produced in the core during the very last stages. Instead, the luminosity that photons carry can remain nearly steady, even as the core reacts more energetically to maintain support against gravity. This decoupling is a marked feature of late evolution, and helps explain why spectra of very evolved hot stars can look steady while their interiors change more rapidly. In a class as extreme as WO-type stars, the interior composition inferred from the surface and from spectral modelling points, to a core where oxygen and heavier elements are abundant. The presence of strong high ionization oxygen lines in the spectrum and the weakness or absence of hydrogen supports that reading. However, the exact central state, whether oxygen or silicon is currently active, cannot be fixed directly from light, because those zones are buried, and because their signals are carried outward only indirectly through the pressure and energy they supply. As a result, statements about the active burning stage remain model-based and are presented with caution. The neutrino-dominated cooling and the steep temperature sensitivity of the reactions leave one additional imprint on the shells. They are thin in radius and sharp in their boundaries. Where temperature falls even slightly below the threshold for a given network, the reaction rate drops steeply and the shell ends. This sharpness helps keep the onion-like order distinct even in a star where radiation pressure is strong. It also means that small adjustments in pressure or temperature caused by changes in composition or opacity can move a boundary by a modest fraction of the stellar radius in short order, rebalancing the set of shells without dramatic external signs. The gravitational field that shapes the shells is set by the mass enclosed. In a compact massive core, the acceleration of gravity grows toward the center, and the pressure needed to support each layer rises accordingly. The temperature follows that requirement, because thermal pressure and radiation pressure together counter the inward pull. In the deepest layers, if electron degeneracy grows, the pressure becomes less sensitive to temperature, and the structure tightens. Even so, under the conditions relevant for a very hot luminous object of this class, radiation pressure remains significant and continues to influence the thickness of the shells and the transport in the overlying envelope. Across all shells, nuclear statistical physics governs the reaction pathways and the composition evolves as elements are built and rearranged. Material processed in these zones will later be carried outward by the wind or will remain locked in deeper layers until a later event unbinds it. In the present view, the important point is that the interior already bears the marks of advanced processing. The shells do the work of turning the products of helium burning into heavier nuclei, and they do so in a structure whose signals reach the observer only through the steady luminosity and the surface mix that the wind reveals. That mix is oxygen-rich, consistent with late burning, and a deeply stripped state, and the maintenance of that mix in the outflow indicates that the shells continue to operate beneath a stable radiative envelope that feeds the wind without sudden changes in the energy it must carry. At the center lies a compact region where pressure, temperature, and density reach their highest values, and where nuclear reactions proceed through the most demanding networks. The geometry is simple, even if the physics is rich. Nested shells surround a small core that holds a large fraction of the mass. Conditions keep matter fully ionized and compress electrons into a partially degenerate state, so quantum pressure contributes alongside radiation and thermal pressure. The electron chemical potential rises above thermal energies, the photon energy density is enormous, and ions move in a dense bath of radiation and electrons that sets the stage for reactions among medium-mass nuclei. Energy transport within this region proceeds mainly by radiative diffusion, because the mean free path of photons is extremely short, and the radiation field behaves like a fluid whose pressure and energy density enter the mechanical balance. The diffusion time across the core remains short compared with evolutionary times at this stage, so hydrostatic equilibrium is a good approximation at each moment. Neutrino emission, however, is a dominant sink in the hottest, densest zones. Neutrinos arise through several channels, pair processes where photons create an electron and a positron that annihilate into neutrinos' plasma processes, where collective electron motions emit neutrinos, and weak interaction chains that convert nucleons and release neutrinos. Because neutrinos escape almost unhindered, they carry energy directly out of the core and do not contribute to the outward light seen at large distance. Their presence forces higher nuclear reaction rates to sustain the central pressure support, while leaving the photon luminosity that crosses outer layers comparatively steady. The composition of the deep interior reflects the ashes of earlier burning and the products of current reactions. Oxygen and neon are abundant where carbon has been consumed, silicon and sulfur grow where oxygen burning proceeds, and in the hottest part of the core, the reaction network of silicon burning may drive matter toward a mixture near the ion group. In that regime, the interconnected web of photodisintegration captures and rearrangements tends toward a statistical mixture that shifts slowly with temperature, not a single fixed product. This state is called nuclear statistical equilibrium, and it emerges only in the very hottest zones. Outside that kernel, incomplete burning leaves a graded pattern of intermediate mass elements. The mechanical balance against gravity follows the equation of hydrostatic equilibrium, in which the gradient of the total pressure offsets the weight of overlying matter. Electron degeneracy provides stiffness that resists compression. Radiation, pressure adds directly to the support, and ion gas pressure contributes the remainder. The combined equation of state produces a high sound speed and a small pressure scale height, so density rises steeply inward across a modest radial span, while temperature climbs more gently than in a purely gas-dominated star. Entropy per baryon remains relatively low because degeneracy limits accessible microstates for electrons, even while radiation stores large energy density. The adiabatic index, which measures how pressure responds to compression at constant entropy, trends toward values characteristic of a mixture dominated by radiation and partially degenerate electrons, a combination that influences stability and the thickness of active zones. Energy generation in the central region depends very sensitively on temperature. In silicon burning, a small temperature increase accelerates the network markedly, so local heating can concentrate in narrow layers. That sensitivity favors convective transport within the deepest active zone, when buoyant motions can carry heat more effectively than diffusion across steep gradients. Many models therefore include a convective kernel inside the hottest layer even when the surrounding envelope is radiative. Outside that kernel, where temperature sensitivity and local heating are weaker transport switches back to diffusion and the stratification remains stable. The convective part of the core mixes composition within its own boundaries, keeping abundances nearly uniform there while leaving sharp gradients at its edges. Those edges coincide with places where reaction networks change dominance, and their sharpness reflects how quickly rates drop when temperature falls. Rotation, if present, introduces mild departures from spherical symmetry, but remains a small correction to the mean structure because the core is compact and dense. Weak differential rotation at shell interfaces concede limited shear mixing that smooths composition gradients slightly, without overturning the layered arrangement. Magnetic fields, whether inherited from earlier evolutionary phases or generated by dynamos inside convective zones, may thread the core. In these conditions, they add only a small pressure component guiding local motions rather than reorganizing the global balance. Direct measurements of fields under such extremes are not available, so their role is treated conservatively in models and bounded by how well calculated spectra match observations that depend on boundary conditions set by the interior. Thermodynamic and transport quantities in the core show clear patterns. The photon luminosity carried outward across inner spheres remains nearly constant with radius, because local sources and sinks balance on scales small compared with the size of the core. Aside from the energy drawn away by neutrinos in the hottest kernel, the heat capacity of the mixture reflects contributions from ions radiation and degenerate electrons, and the strong temperature sensitivity of reactions in the center implies that small structural adjustments can re-establish balance rapidly after local changes in rate. The electron capture threshold on certain nuclei may be crossed in the innermost zones, as density climbs changing composition by converting protons within nuclei to neutrons and emitting neutrinos that carry energy away. Such captures reduce the number of electrons per baryon and therefore the degeneracy pressure, prompting a compensating rise in temperature and reaction activity to preserve equilibrium. The extent of these processes depends on the exact density and temperature, and present information supports only a general description that they become relevant in the deepest layers of very evolved massive cores. The coupling between central burning and the atmosphere above is indirect, so observables at large distance track averages rather than instantaneous core changes. The wind and the emitting envelope respond to the steady photon luminosity that the core and inner shells supply after neutrino losses are accounted for. As a consequence, spectra can look calm and persistent, even while the inner composition drifts from oxygen dominated towards silicon enriched, and then toward a mixture nearer the iron group. This separation of timescales is a hallmark of advanced evolution. Inside the core, the state remains quasi-steady. Hydrostatic balance holds. Diffusion carries photon energy outward. Neutrinos drain heat directly, and nuclear networks proceed within narrow zones set by temperature and density. Outside, the core shells process the ashes in ordered layers and deliver a nearly constant radiant flux to the envelope. The present description therefore sets the central region as a compact high-temperature, high-density domain, supported by a mix of electron degeneracy and radiation pressure, cooled primarily by neutrino emission, and engaged in nuclear burning among intermediate and heavy nuclei within networks, whose equilibrium character strengthens toward the center. It is bounded by sharp stratification. Where reaction families change, it contains a small convective kernel where sensitivity to temperature demands rapid transport, and it maintains conditions that allow the surrounding shells and envelope to remain in their own steady balances, while the wind above carries the star's processed material into space. Elemental yields appear in the spectrum as clear signatures of processed matter, leaving the star in its fast wind. The dominant products are carbon and oxygen made during helium fusion, with helium itself still present but greatly reduced compared with an unevolved surface. The ratio of oxygen to carbon is high for this class, and the specific mix fixes which ions shine most strongly across optical and ultraviolet bands. Very highly ionized oxygen produces conspicuous features at short wavelengths, and strong carbon, in high stages of ionization, shapes wide lines at longer visible wavelengths. Helium in a doubly ionized state supplies a smooth background of recombination light, but contributes less to the most prominent broad features than carbon and oxygen do. These spectral weights are not merely markers of temperature. They are direct evidence that the outer layers have been stripped down to fusion ashes. In helium burning, 3 helium nuclei combine to make carbon, and then carbon captures helium to form oxygen. If burning proceeds long enough and density and temperature remain high, further captures enrich neon and magnesium in deeper zones. When a wind carries material from those layers into space, the composition at the base of the outflow can include traces of neon and magnesium in addition to the dominant carbon and oxygen. Observations of infrared fine structure lines in some similar stars show enhanced neon consistent with this chain. The exact strength of those lines depends on density in the forming region, and on how quickly the wind thins with radius, but the presence of neon above levels expected from unprocessed gas is a robust sign that helium burning has advanced. The wind returns these elements to the surrounding medium in a steady stream. Mass loss is continuous and carries momentum and energy as well as composition, so each parcel that leaves mixes into the ionized environment described earlier and then drifts outward to join the interstellar gas. Mixing is not immediate. At first, the wind occupies a hot cavity bounded by a shell of swept-up gas. Within that cavity, the composition remains close to the original wind values, so any cooling emission from the interior has abundances that reflect the star. Over time, small breaches and mixing layers at the contact surface move material across the boundary, and turbulence blends wind material with the ambient gas. The result after long mixing is an enhancement of carbon and oxygen in the local interstellar medium, with small increases of neon and magnesium where those were present in the wind. The overall enrichment per unit time follows from the product of mass loss rate and composition, because density falls with radius. As the inverse square, the concentration of enriched gas decreases outward, yet the total mass added to the surroundings grows steadily as the flow continues. Where the bubble interacts with denser clouds, the enriched material can be mixed into those clouds' edges, altering the local ratios of heavy to light elements that future generations of stars will inherit. The spectrum records these yields through line ratios that compare ions of carbon and oxygen across a range of excitation. Pairs of transitions from different stages of the same element act as thermometers and barometers, while ratios of carbon to oxygen lines trace relative abundance once the temperature and density are fixed by other diagnostics. Because the wind is clumped, analyses treat emissivities with a clumping factor, so that derived abundances and mass loss rates remain consistent. Even with this correction, the oxygen-rich nature of this class stands out, and the weakness of hydrogen features and the relative faintness of helium lines put strong model-independent limits on their fractions. Isotopic fingerprints can in principle add detail to the yields. Helium fusion followed by secondary reactions in earlier phases enhances the isotope neon-22 by transforming nitrogen from prior hydrogen, burning through a chain that passes through fluorine and oxygen before landing on neon. In cooler carbon-rich stars, neon-22 can seed neutron production that drives a weak, slow neutron capture process, nudging iron group seeds toward elements like strontium and yttrium. In this very hot class, the environment near the surface is hostile to dust and to molecule formation, so isotopic measurements through molecules are not available, and any weak, slow process products are not directly seen in the spectrum. Even so, models that match the helium burning history and the observed carbon and oxygen abundances indicate that neon-22 should be present above the unprocessed baseline, and that conclusion aligns with the occasional detection of neon lines stronger than expected. Dust formation is rare under these conditions. Carbon-rich cooler members of the broader family can condense dust in their winds, where temperatures and densities allow grains to grow. Here the gas is too hot and too strongly ionized, and the mix is oxygen-rich rather than carbon-rich at the relevant radii. Without grains, heavy elements remain in the gas phase, and are mixed into the ionized bubble and the ambient medium as ions and atoms rather than as solids. This difference matters for how quickly yields become part of later star-forming material, because solid grains can survive shocks and travel farther before being destroyed, while gas phase ions mix more promptly with the local plasma. The yields influence the cooling of the surrounding gas. Carbon and oxygen provide efficient radiative losses through collisionally excited lines. As the enriched wind material mixes into the shell and the nearby medium, those lines become brighter for the same temperature and density than they would be in unenriched gas. The change feeds back on structure because higher cooling efficiency can thin hot layers more quickly and can sharpen the boundary between warm ionized gas and cooler, denser zones. In regions where dense clumps survive, the added carbon and oxygen increase the tendency for those clumps to cool and compress, aiding the survival of neutral skins on their shaded sides. Across the electromagnetic spectrum, the fingerprints of yields appear in consistent ways. In the ultraviolet, very high excitation lines of oxygen mark the most strongly ionized gas close to the star. In the visible, broad features from carbon and oxygen dominate the line budget and display profiles that reflect wind speeds. In the infrared, fine structure lines from oxygen and neon trace densities farther out, and help calibrate abundances because their formation depends less strongly on temperature than optical lines do. Radio continuum measures the square of density integrated along the line of sight, and therefore anchors mass loss in a way that is largely independent of abundance once the mean charge per ion is fixed by the observed mix. Combining these bands ties composition density and wind speed into a coherent picture of what the star returns to its environment. The total mass of heavy elements carried away during this present stage depends on how long the wind persists at its current strength. That duration is constrained by evolutionary calculations and by comparisons to other members of the same class that show similar temperatures and compositions. While exact values are model-dependent, the steady nature of the observed spectrum and the lack of large-amplitude photometric changes indicate that the outflow maintains a near-constant character on timescales accessible to monitoring. Under such conditions, the integrated yield over many thousands of years is significant even if the mass loss rate at any moment is modest, compared with the mass of the star. Each year adds a small amount of carbon and oxygen to the surroundings. Each century adds a measure that neighboring clouds can register. Each longer interval builds a local enhancement that broad surveys can detect statistically in associations where many such stars contribute. The star's yields also alter the ionization balance in its neighborhood. High fractions of carbon and oxygen in the gas increase the opacity in the ultraviolet line forest, which strengthens the coupling between radiation and matter in the wind and maintains high acceleration efficiency. In the surrounding ionized medium, those same elements provide cooling that sets the temperature near the familiar range for photoionized gas, and thus stabilizes the outer emission region. The interplay of abundance, opacity, and cooling keeps the larger structure in a steady state, in which radiation from the star and the composition of the gas reinforce one another to produce the observed line intensities and profiles. In this way, the yields are both a record of interior processing and an active agent in shaping the appearance of the volume around the star. Variability in this kind of star arises from the flow of its wind from small departures from spherical symmetry and from slow changes that accompany late evolutionary stages, and each operates on a different timescale. The fastest signals ride on the outflow itself. The acceleration from the base to near terminal speed occurs over only a few model radii, so the time it takes a parcel of gas to travel from the inner line forming zone to the outer emission region is measured in hours to days for the speeds inferred from broad profiles. As clumps form, merge, and drift outward, they imprint migrating subfeatures on strong lines that move steadily from shallow blue shifts to deeper ones. High-resolution monitoring resolves these drifts and shows a pattern of ripples that is consistent with parcels being accelerated by line pressure. The fluctuations are modest in amplitude, and they do not demand any deep structural change. They are the natural consequence of an unstable line-driven wind in which local density and velocity perturbations feed on the radiation field. Very soft X-rays vary on similar short timescales, because weak shocks form when faster clumps run into slower ones and heat small pockets of gas. Cooling times at those densities are short, so the emission brightens and fades as shocks appear and dissolve while the mean wind remains steady. Photometric changes in visible light tend to be small. The continuum emerges from a large depth range through a scattering-dominated envelope, and many independent zones contribute so small local changes average out. Low-amplitude flicker can still be detected with precise instruments, often correlated with the movement of subfeatures in lines, but large swings are not characteristic. Polarization is likewise low and varies gently when present, placing limits on large-scale asymmetry in the envelope. Any rotation of the star adds a longer clock to the variability pattern. Rotation can imprint a slow, repeating modulation if broad wind structures such as spiral density enhancements co-rotate close to the base. In other hot luminous stars, such correlating interaction regions can produce a weak recurrent pattern in line profiles. For this class, the evidence points to only smaller symmetries on large scales, so any rotational signature would be low in amplitude and may be masked by the stronger irregular signal from clumps. If a period exists, it is expected to be measured in days rather than in hours, but present constraints leave a wide range and emphasize that firm periods are difficult to secure in winds dominated by stochastic structure. On intermediate timescales, months to years, the overall strength of broad lines and the radio-free continuum are useful checks on stability. The radio continuum scales with the square of density integrated along the line of sight, and is sensitive to the total amount of ionized gas in the outer wind. Measurements over many seasons in stars of this class generally show only small drifts that fall within uncertainties once clumping is considered, supporting the picture of a persistent outflow with a nearly constant mass loss rate. Optical and ultraviolet lines show comparable steadiness in their total equivalent widths, even as their detailed shapes ripple again, consistent with a wind whose average properties change little, while small-scale structure evolves rapidly. The outer bubble where the fast wind meets the surrounding gas evolves on still longer timescales because its radius and expansion speed respond to the integrated momentum and energy supplied by the wind. Expansion speeds of a few dozens of kilometers per second and radii of many light years imply dynamical ages of many thousands of years. Over human observing spans, subtle brightening along rims or slow motions of knots may be detected with careful imaging, but the global shape and size remain essentially fixed. This slow outer evolution provides an independent cumulative record of how steady the wind has been. A clean round shell suggests persistent driving, while stronger symmetries point to ambient gradients, or to past changes in output. Beyond observational clocks lie the evolutionary timescales set by nuclear burning in the interior. At late stages, the duration shortened dramatically compared with the long eras of hydrogen and helium burning. Model sequences for massive stripped stars place the carbon burning phase at roughly many thousands of years, neon burning at roughly years, oxygen burning at roughly months to a year or so, and silicon burning at roughly days. The exact values depend on mass composition, and the details of energy loss through neutrinos and different calculations give overlapping but not identical ranges. What matters for observable steadiness is that even the shortest of these timescales remains long compared with the flow time through the wind and with the time required for radiation to diffuse across the inner envelope. As a result, the photon luminosity supplied to the atmosphere can remain nearly constant, while interior shells proceed through their stages because neutrino cooling drains much of the additional power in the center without altering the outward light. The effective temperature inferred from spectral modeling reflects that steady luminosity in the structure of the envelope rather than moment-to-moment changes in the deepest reactions, so it also remains within a narrow band when measured over years. The timescale that links the inner boundary of the line-forming regions to the changing conditions below is the thermal timescale of the envelope, the time required for that optically thick layer to adjust its temperature structure if the input luminosity were to change. In a compact radiation-dominated envelope, this timescale is short compared with the evolutionary times of the burning shells, but long compared with the wind acceleration time. Because the input remains steady within small margins, the envelope does not undergo large thermal readjustments, and the boundary conditions that set the wind continue to hold. This hierarchy of timescales explains why spectra of such stars can look calm over years while their interiors advance through late burning. Uncertainties in variability analysis arise from the same conditions that make the wind luminous. Clumping raises the emissivity of density-dependent diagnostics, and complicates any attempt to track absolute mass loss from a single line or band. Analyses therefore use combinations of lines' continua and wavelengths to factor out density effects. Electron scattering wings which respond to column density rather than to density squared help anchor models alongside radio measurements that depend on the outer wind. Repeated campaigns across seasons ensure that any slow drifts are distinguished from calibration differences. In the ultraviolet, where the most highly ionized species shine sensitivity to instrumental settings, and interstellar absorption requires careful cross-checks to avoid mistaking instrumental changes for intrinsic variability. On the evolutionary side, uncertainties follow from composition mass and prior history. A difference of only a small fraction in mass at the start of a given stage can shift the duration of that stage by a large factor, because reaction rates rise steeply with temperature. Likewise, the degree of prior mass loss changes the core mass and the envelope structure, and therefore the luminosity that must be carried outward. These uncertainties are communicated as ranges with clear caveats, and statements that a given stage is ongoing remain conservative because no direct probe can reach the core. The global picture, however, is coherent. Short timescales belong to wind structure and produce migrating ripples and soft X-ray flicker. Intermediate timescales belong to slow modulations that would accompany rotation or gradual drift in mass loss, but are often small or absent within measurement limits. Long timescales belong to the wind-blown bubble and to the interior burning stages that set the overall luminosity, yet leave the observable spectrum mostly unchanged across human spans. In this layered timing, each clock runs at its own pace and records a different facet of the star's state. And the combined record is a stable high-temperature source whose day-to-day face is governed by its wind, while its deeper changes unfold over years to millennia. Comparison within the small family of oxygen sequence Wolf-Rayet stars places this source among objects that share extreme temperatures, stripped compositions and very fast winds, yet differ in details that reflect both intrinsic diversity and measurement limits. The class itself is rare. Surveys that sift the galactic plane and nearby galaxies find only a handful of candidates whose spectra display the strongest high-excitation oxygen lines, alongside broad carbon features and weak helium. Those spectra come from expanding highly ionized envelopes, rather than from stable thin photospheres, so the usual temperature scales that work for cooler stars do not apply directly. Instead, effective temperature is a model-dependent summary derived from fitting the full spectrum with non-local thermodynamic balance atmospheres that include thousands of lines electron scattering and an outflow velocity field. Published values for members of this class cluster around a range from roughly 150,000 to a little above 200,000 Kelvin, with the hottest estimates reaching toward the upper end of that interval. The star under study sits at or near that upper bound in most analyses, while close cousins such as the compact oxygen-rich stars in Cygnus and in the Carina Arm occupy similarly high territory within their error bars. Differences of a few tens of thousands of Kelvin in those fits often traced to choices about clumping factors, wind velocity laws, and the exact treatment of line blanketing in the ultraviolet, rather than to firm resolved disparities in the underlying radiation fields. Terminal wind speeds also fall within a narrow band across the class. Broad emission lines with extended wings indicate outflows that reach several thousands of kilometers per second, and profiles with rounded tops and electron scattering skirts of comparable shape appear in many members. Some objects show slightly broader wings or deeper blue side hollows in particular lines, suggesting modest differences in acceleration profiles or occultation by the inner wind, but most sit within overlapping ranges once viewing geometry and clumping are considered. Mass loss rates when corrected for clumping also agree within factors of a few, and those factors match the spread expected from uncertainties in density diagnostics that scale with density squared. Composition is a more robust axis of comparison. The oxygen-to-carbon ratio in this class runs high compared with carbon-sequence Wolf-Rayet stars, and helium is weak. Ratios of specific oxygen-to-carbon lines in the optical and ultraviolet align with models that require a surface rich in oxygen, consistent with deep helium-burning products exposed by severe stripping. Neon lines appear in the infrared in some members at strengths above unprocessed expectations, supporting the chain in which nitrogen from earlier hydrogen burning transforms through helium burning to enriched neon. The presence or absence of particular neon and magnesium features across the class depends on density and on how strongly different ions are populated in the outer wind, so comparisons use matched wavelength coverage and similar analysis methods to avoid bias. Across galaxies, environmental differences add another dimension. Oxygen-sequence stars in the Milky Way in the Large Magellanic Cloud and in the Small Magellanic Cloud share their basic spectral character, yet metallicity gradients change the forest of ultraviolet lines that both drive and absorb. Lower metallicity reduces the number and strength of available lines, which can alter wind acceleration efficiency and mass loss rates. Observations suggest that while the class persists in lower metallicity, environment's winds may be slightly weaker on average for comparable luminosity, and terminal speeds show mild shifts. These trends are subtle and require careful cross-calibration, because distance crowding and foreground extinction change from field to field, and because the rarity of the class limits sample sizes, polarization and interferometric constraints on geometry likewise show broad agreement. Most oxygen sequence stars present small continuum polarization, consistent with outflows that are close to spherical in their larger scale shape. Occasional low amplitude, slowly varying polarization hints at minor asymmetries or at weak rotational modulation in a subset, but no strong persistent departures from spherical symmetry appear as a rule. Interferometric measurements at optical or near-infrared wavelengths rarely resolve the continuum emission region, because it spans only a few model radii, yet differential size changes across strong lines have been reported in a few bright cases, consistent with formation farther out, where the flow is more extended. This behavior matches general predictions of outflowing atmospheres and does not separate members sharply from one another. Time variability patterns align across the class as well. Migrating subfeatures in broad lines move from small to large blue shifts over hours to days recording clumps that accelerate outward. Soft X-ray emission at very low levels accompanies these winds and flickers gently as shocks appear and cool. Photometric stability in the visible holds within small margins and radio-free continua vary only weakly when measured over seasons. A minority of objects show hints of repeating modulation that could reflect rotation or stable wind structures, but the amplitudes remain low, and the periods, if present, lie in the range of days, not hours, and are uncertain. Members embedded in complex environments differ mainly in how clearly their wind-blown bubbles can be traced against cluttered fields, not in the intrinsic flow that builds those bubbles. Classification boundaries between oxygen sequence stars and very hot members of the carbon sequence can blur in individual cases when signal-to-noise is modest or when extinction removes key bands. Reclassification has occurred for a few objects as beta spectra revealed line ratios more clearly. In such cases, the underlying physics remains the same: a stripped, very hot star with a fast wind and a surface composition set by helium burning. The label shifts to reflect which lines dominate, and effective temperatures are revised within the same general range. This fluidity underscores that the class occupies the highest temperature, most oxygen-rich corner of a broader family, rather than standing as a wholly separate phenomenon. Comparisons with even more extreme candidates reported in the literature also require caution. Occasionally a source is proposed as hotter based on a limited set of lines, or on very hard radiation inferred from surrounding nebulae. Follow-up modelling that includes line blanketing and clumping frequently reduces those extreme values into the common band. Conversely, some members may be slightly hotter than currently quoted if future models incorporate improved opacities or larger line lists. The differences are typically within a few tens of thousands of Kelvin and do not overturn the shared picture of a class clustered at very high effective temperatures. Distance and extinction uncertainties contribute additional spread when luminosities are compared. For galactic sources, foreground dust along low-latitude sightlines can redden and dim the continuum in ways that depend on grain properties and on small-scale structure in the interstellar medium. Correcting those effects introduces ranges in absolute magnitude that feed into derived radii and mass loss rates. Extragalactic members benefit from more secure distances, but can suffer from crowding and from unresolved companions or clusters that contaminate broad-band fluxes. Across these complications, careful spectroscopy remains the anchor for class-level comparisons, because line ratios and profiles depend on local conditions in the wind and are less sensitive to absolute calibration. The shared properties of the oxygen sequence group therefore emerge clearly under consistent analysis. Very high effective temperatures summarized by models that include outflowing atmospheres, fast line-driven winds with broad emission features, and electron-scattering wings, oxygen-rich and helium, poor compositions with carbon as a strong second component, small polarization, and low amplitude variability that reflect near-spherical large-scale geometry, and weak or absent dust under present conditions. Within those common traits, individual differences persist that trace environmental metallicity, subtle variations in acceleration laws, and the inevitable measurement uncertainties that attend rare, faint and crowded targets. Set against this backdrop, the star under study is representative at the extreme hot end. By most modern fits and shares, the line shape's ionic mix and variability character that define the class. The position it occupies in parameter space is supported by the same diagnostics: ultraviolet and optical line ratios, broad profile curvature, radio continuum slopes, and the lack of strong polarization that place its peers along a narrow ridge of temperature and composition. The present state points back to a massive progenitor that forms in a dense star-forming region and begins life as a hot luminous star with a hydrogen-rich envelope and a convective core that burns hydrogen by chains that produce helium and leave behind nitrogen. In that early phase, the surface shows the imprint of CNO processing only if mixing is strong, but in many cases the outer layers remain near their birth composition while winds carry away a modest amount of mass. As evolution proceeds, helium accumulates in the core, the star brightens, and the ratio of radiation pressure to gravity rises. Rotation, if present, circulates material between deeper and shallower layers, and can prolong the main phase of hydrogen burning by feeding fresh fuel into the core. When hydrogen in the core is exhausted, the star readjusts to burn hydrogen in a shell, while the core contracts and heats until helium ignition begins. From that point, pathways diverge according to mass rotation metallicity and whether the star remains single or belongs to a binary. In a single star with very high initial mass and near solar metallicity, strong line-driven winds peel back the outer layers during the late hydrogen shell and helium core burning phases. The surface composition moves from hydrogen-rich toward helium-rich as mass loss and internal mixing reveal deeper matter. Spectra in that stage match the nitrogen sequence of Wolf-Rayet stars when helium and nitrogen dominate at the surface and when carbon and oxygen are still confined below. Continued mass loss exposes layers that have seen helium fusion, and the surface becomes carbon-rich. The spectrum then matches the carbon sequence. As helium burning advances, carbon captures helium and enriches oxygen in layers just above the core. With further stripping, the surface shows strong oxygen and diminished carbon, and the spectrum moves into the oxygen sequence. In that single star channel, the present class marks the endpoint of a sequence Wn to Wc to Wo, driven by luminosity-powered winds that are strongest at high metallicity, where many lines are available to absorb momentum. A second channel involves binary interaction. In a close pair, the initially more massive star expands during late hydrogen burning and fills its gravitational lobe, transferring mass to the companion. If the exchange is stable, the donor loses much of its hydrogen envelope to the companion and becomes a helium star long before winds alone could have removed that mass. If the exchange becomes unstable, a shared envelope phase can eject the outer layers rapidly and leave a tightened pair or a merger product with a stripped surface. In both paths, the mass that remains around the core is small, and helium burning proceeds under strong radiation pressure with little hydrogen above. Subsequent winds carry away additional mass, and the surface composition follows the same exposure sequence from helium and nitrogen toward carbon and then oxygen. Observational comparisons suggest that both channels operate in nature. Associations rich in massive stars show many binaries, and evolved helium stars and compact remnants in pairs attest to past interactions. At the same time, very luminous isolated Wolf-Rayet stars exist in fields where a single star path is plausible. For individual objects, distinguishing channels is difficult because the present spectrum depends mainly on current mass luminosity and surface composition, rather than on the detailed history of how the envelope was removed. Constraints come from the presence or absence of close companions from the motion of the star relative to nearby clusters and from the total angular momentum implied by any rotational signals in the wind. In the single-star picture, metallicity matters for the efficiency of line-driven mass loss. Higher metallicity provides more ultraviolet lines to absorb momentum and amplifies winds favoring full stripping without binary help. Lower metallicity weakens winds and makes binary interaction more important for exposing helium and then carbon and oxygen layers. Observations of oxygen-sequenced stars in the Milky Way and in nearby lower metallicity galaxies show that the class appears across environments, though the relative fractions may shift. That distribution supports a mixed origin in which both strong winds and binary mass transfer can lead to the same present state. Rotation adds another dimension. Rapid spin circulates material through meridional flows and turbulence that blend fresh fuel into the core and carry processed material outward. In very fast rotators at low metallicity, almost homogeneous evolution can occur, keeping the star compact and hot throughout hydrogen burning and accelerating the arrival at a stripped helium-rich stage even without extreme mass loss. Whether such evolution contributes significantly to the present object depends on how much rotation remains after envelope removal and whether signatures of rotational modulation exist in the wind. The low polarization and weak periodic signals seen in many oxygen-sequenced stars suggest that strong persistent rotational asymmetry is uncommon at present, although rotation in earlier phases may still have influenced internal mixing and mass loss. The path through earlier Wolf-Rayet stages leaves traces in the ambient medium. A nitrogen-rich shell at large radius can record an earlier WN wind, while an inner carbon-enriched layer can mark a WC stage. In cluttered galactic fields, separating such relics from unrelated structures is challenging, and a clear chemical stratification across multiple shells is rarely established. Even so, the expectation from models is that the surroundings may hold a fossil record of changing yields if expansion speeds and densities permit survival of older layers. The timescales of the earlier phases set the chance of preserving such clues. The hydrogen-burning lifetime of a very massive star spans a few million years, long enough to inflate a cavity with a layered, swept-up rim. The helium-burning phase lasts a fraction of that time, yet still exceeds the tens to hundreds of thousands of years needed to expand a distinct inner shell. Later stages shorten dramatically, and the present phase, being late and stripped, occurs against the backdrop of structures built earlier. In a binary channel, kicks from prior mass exchange or from a companion's explosion can displace the star from its birth site, complicating any attempt to tie relic shells to present position. Considering the interior, the present surface composition implies that the core mass is set mainly by the original star's mass, and by how much of the envelope was removed before helium exhaustion. More massive progenitors build larger cores and reach higher luminosities at given effective temperatures. The observed high temperature and strong oxygen lines point toward a core that has passed well beyond helium burning, and that sits beneath a thin, hot envelope whose mass is small relative to the remnant. Models connect these properties through grids that vary initial mass metallicity rotation and binary history, and then compute surface compositions and spectra at each step. Where such grids match the observed mix and wind characteristics, they point back to initial masses in the high range, typical of very luminous early-type stars reduced by mass loss and transfer to the small present envelope. Uncertainties remain. The exact strength of winds during the late main sequence and early helium-burning phases depends on clumping and on the treatment of line overlap in the ultraviolet, both of which affect how fast a single star can strip itself. Binary interaction outcomes depend on the response of the donor's radius to mass loss, and on the efficiency with which orbital energy expels a shared envelope both of which are mediated by uncertain physics in rapidly changing optically thick flows. Rotation-driven mixing depends on prescriptions for angular momentum transport inside stars, which are tested indirectly against surface abundance patterns and against the distribution of rotational speeds observed in young clusters. Because of these uncertainties, progenitor histories are presented in families rather than in unique lines. Even within those bounds, a consistent picture holds. A very massive star burns hydrogen in its core and sheds mass. It ignites helium and continues to lose its envelope until helium-burning products reach the surface. It passes through a nitrogen sequence stage if some hydrogen remains, and the surface is helium and nitrogen rich, then moves into a carbon sequence stage as helium-burning ashes appear, and finally enters an oxygen sequence stage when oxygen rises and carbon falls at the surface. The present spectrum dominated by very highly ionized oxygen and carbon, with weak helium fits that last stage. Whether the envelope reached this point through winds alone, through binary stripping, or through a combination, the physical state now follows from the same ingredients: a small hot radiative envelope, above a compact core, a fast line-driven wind that carries oxygen, rich material outward, and a layered interior in which advanced burning proceeds, while neutrino losses keep the outward luminosity steady. In the near term, the energy flow from the interior remains steady and light, even as late burning proceeds beneath the envelope, so the wind continues to carry oxygen-rich material outward at high speed, and the radiation field continues to ionize the surroundings. The envelope, supported by radiation and thinned by prior mass loss, offers little inertia against change, yet the boundary conditions at its base vary only slightly, because neutrino cooling in the deep core drains much of any additional power before it can appear as photons. The outflow therefore persists with similar terminal speeds, similar clumping, and similar broadline profiles, and the continuum maintains the same scattering softened shape. On timescales of years, the observable phase shifts mainly through the movement of clumps and the gentle breathing of line wings. On timescales of thousands of years, the wind-blown cavity records the accumulated work of the flow as it expands, mixes, and adapts to gradients in the surrounding gas. The environmental impact unfolds along three coupled channels: radiation that keeps large volumes ionized and warm, mechanical driving that sweeps, compresses, and stirs, and chemical enrichment that changes cooling and future cloud behavior. Radiation from the hot compact envelope bathes nearby gas in photons, capable of stripping electrons from common atoms out to distances fixed by the balance between ionization and recombination. In low-density corridors, the ionized zone can reach far and remain nearly transparent, while in denser patches the front stalls wraps around clumps and sculpts pillars and bright rims. The temperature in ionized volumes settles near 10,000 Kelvin a level, set by the trade between photoelectric heating and line cooling, and that temperature keeps sound speeds high enough to smooth small irregularities, but low enough for pressure contrast to survive around dense knots. The wind's mechanical work builds and maintains the layered bubble. Inside the termination, shocked wind fills the cavity with very hot rarefied plasma that emits soft X-rays and presses on the shell. At the contact, discontinuity shear and rippling instabilities mix a fraction of wind material into the swept-up layer, and heat leaks through conduction and through turbulent exchange. The shell itself cools to a few times 10,000 Kelvin, where radiative losses are efficient and its thickness reflects the interplay between cooling pressure and momentum supply. Where the bubble meets a density rise, it slows and brightens. Where it meets a drop, it accelerates and can break out venting hot gas into larger tenuous volumes. These asymmetries feed back on the ionized region because the geometry of the shell, sets where radiation escapes most easily and where it is intercepted. Chemical enrichment accompanies both channels. The wind carries carbon-oxygen and traces of neon and magnesium into the cavity and then into the shell through mixing layers. In the shell, those elements increase cooling efficiency, making the compressed gas radiate more strongly for the same density and temperature. Over long spans, this encourages the condensation of denser patches in otherwise marginal gas and can assist the survival of neutral skins on cloud faces that are partly shielded. In the larger interstellar medium, the accumulated mass of enriched gas diffuses outward as the shell erodes and as the cavity merges with surrounding structures, adding to the reservoir from which later generations of stars form. The practical reach of these changes depends on the ambient conditions into which the bubble expands. In a crowded intergalactic field crossed by filaments and older shells, boundaries meet and overlap. Shocks from other sources can cross the region and re-energize or shred the shell. Where two bubbles meet, a new contact surface forms, and the mixed layer between them can host thin cooling sheets that fragment into knots. Magnetic fields thread all of these zones and add tension that guides filaments, resist sharp bends, and organizes the direction of the thinnest structures. Polarization maps of aligned grains would show the field draped around the outer shell, and rotation measures through the cavity would rise, where plasma densities and field strengths combine along the sightline. The wind also contributes to high-energy particle populations at its shocks. Where the termination shock or the outer forward shock is sufficiently strong and irregular, charged particles can gain energy by scattering back and forth across the shock fronts. In this environment, the shocks are fast and the magnetic field is structured conditions that can support some acceleration, though the efficiency in such hot low-density plasmas remains uncertain. Any non-thermal emission produced would be faint compared with the strong thermal line and continuum signals, and its detection would require sensitive, well-targeted observations. Dust in the region responds to both radiation and shocks. Close to the star grains cannot survive, but at greater distances the shell and the illuminated faces of protruding clumps hold dust that absorbs ultraviolet light and re-radiates in the infrared. Grains in the outer shell can be shattered or eroded by shocks, changing the size distribution and altering how extinction behaves across wavelengths in the local field. Over long periods, as the bubble grows and slows, dust from outside can drift inward along the edges and seed the mixed layer with solids, but the cavity interior remains largely grain-free until pressure falls and mixing advances. The immediate future of the star itself remains bounded by the late burning stages in the core and by the small mass of the present envelope. The high effective temperature and the oxygen-rich wind persist as long as the envelope maintains its structure, and the inner shells continue to supply steady photon luminosity. Model sequences place the remaining nuclear steps on timescales far shorter than the early life, but still long compared with human observation. Predictions of an exact endpoint and schedule in any individual case carry wide uncertainty because the deepest reactions are hidden, because neutrino cooling decouples core power from emergent light, and because the remaining envelope mass and core mass are not directly measured. In an ensemble sense, stripped very hot oxygen, rich stars are understood as advanced massive star products that will end their lives through core collapse after late burning exhausts nuclear support. But the timing and detailed path for a single source are not fixed by present spectra. Against that uncertainty, the environmental work continues at a measured pace. Each year of steady wind adds a small increment to the cavity's energy and to the shell's mass. Each decade allows the ionization front to nibble at small protrusions and lift photoevaporative flows from clump faces. Each century advances the radius by a fraction of a light year, registering the integral of momentum supply and ambient resistance. The surrounding medium responds slowly, redistributing pressure-bending field lines and adjusting the balance between warm ionized gas and cooler, denser phases. The region thus evolves through a sequence of quasi-steady states set by the interplay of radiation, mechanical driving, cooling, and mixing. On larger galactic scales, the contribution from one such star is small, yet regions with many massive stars in overlapping phases build networks of cavities and shells that channel flows of hot gas, establish pathways for radiation to travel and seed star-forming clouds with heavy elements. The present source participates in that collective pattern, along a line of sight crowded by dust lanes and stitched with older arcs. Its radiation keeps nearby volumes ionized and warm. Its wind maintains a cavity and presses on the edges. Its composition alters cooling where mixing proceeds. These outward effects complete the circuit that begins with nuclear processing in the core and ends in the interstellar medium, transferring energy and matter step by step through the atmosphere, the wind, the bubble, and the shell into the broader field.